works. So
He might not have.
okay, everyone.
Yeah, but no.
So there was some technical delay, but we are ready to start. Ready to start? Yeah. Okay, today we are very happy to have Sebastian-Phillip from DESY, who's going to tell us about holographic interfaces in symmetric product orbifolds, please.
Yeah. So thank you very much for inviting me and for giving me the opportunity to speak about this subject and about AdS2 branes and AdS3 S3 T4. My plan for the next, I moved on here, but not there. So it turned out to be false that you guys were ready. So yeah, I guess the beginning I can also just talk. So my plan for the next 60 minutes would be to first give you some holographic motivation for the interface construction that is the subject of this talk. Then I will review symmetric product orbifolds, which are the two DCFTs in which the interface live that I'll discuss. And with this background, great, thank you. With this background, we'll then be able to go in detail to the construction of these interfaces, and finally show you some properties of the interface, which ultimately will also create the connection back to the holographic motivation and establish their holographic relevance. And this talk is based on a paper from April with Yasuaki Hikida, my PhD supervisor Volker Schomeros, and Takashi Tsuda, as well as some current work in progress with Volker Schomeros and Takashi. Okay, so let's directly dive into the holographic motivation. So one feature of AdS3 that we all know and love is the strong weak duality. So the string length and the Tuft coupling are inversely related, and this leads to spectacular predictions such that that you can study strongly coupled gauge theory on the boundary with supergravity in the bulk, or vice versa. Very stringy regimes of quantum gravity with perturbative gauge theory. But of course, this also makes correspondence notoriously hard to check, because you never have both sides of the duality, or almost never have both sides of the duality on a full control at the same time. In this context, it's very remarkable that around 2018, 2019, Eberhard, Gabadier, and Gopakuma managed to establish an example where both sides of the duality are simultaneously under full computational control. And I guess many of you will probably also be familiar with this, perhaps from interactions with Andrea, who has also significantly contributed to our understanding of this duality. And it involves strings on AdS3 S3 T4 with the minimal amount of pure NS flux on the bulk, and a grand canonical ensemble of symmetric product orbifolds on the boundary. So I'd like to make 3 comments about this before moving on. So first, where is this in this strong, weak scale? So the bulk is very non-geometric and as stringy as could be, as far away from supergravity as you can imagine. And on the boundary, you just have the free gauge theory. So in particular, it's no big surprise that this side is under good control. What's remarkable is more that the other side of the duality is well understood. Then another comment about this grand canonical ensemble. So symmetric product orbifolds, this sim n are, as I will review, Sn gauge theories, and the n here is the size of the gauge group. And typically in string theory, I suppose you would assume that the dual gauge theory should be some fixed n theory, and you would like to relate n to the string coupling. In this pure NSNS AdS3 examples is slightly different, and instead you need to consider grand canonical ensemble, where you average over the size of the gauge group, and you introduce some chemical potential that is dual to that's ultimately dual to the string coupling, and this is the way that you create the connection to string perturbation theory. And finally, I said that both sides of the duality are under good control, and you can explicitly match quantities. So in particular, the entire closed string spectrum was computed on the string side and matched with the spectrum of local operators and symmetric product orbifold, and also scattering amplitudes of closed strings were matched with local operators, local correlators computed in this grand canonical ensemble. But of course, AdS3 is supposed to be a stronger statement, not only about local operators, but also about non-local excitations. And the question is then, okay, how can we relate non-local excitations across this duality? And as far as I know, the first paper that addressed this question was Gabadier in this particular context, was Gabadier, Knight, and Vosmir in 2021, where they essentially looked at two different families of branes in this AdS3 background. So one family was some instantonic branes whose world volume is completely space-like, and that in particular don't support any dynamical physical open string spectrum. And for these instantonic branes, the authors of that paper managed to identify a holographic dual in symmetric product orbifold. It's just some boundary states of symmetric product orbifold. And the other type of branes they looked at were some AdS2 branes, which actually have a non-trivial time extension. So this in this picture here, where AdS3.
Sorry, AdS2 brane, you mean the brane is on AdS2?
So in this picture here, we have AdS3 as a cylinder, and time goes up.
What
and
kind of
blue
brane?
surface here is an AdS2 subspace of AdS2.
What kind of brane is it?
So
Is it a D brane? Is it a
yeah, it's a D brane.
D what? You
So
don't care, or
okay, I mean, for the purpose of this talk, I mean, what's important is they write down the explicit boundary states of the worldsheet theory that describe these branes, and these worldsheet theory states are essentially gotten by studying symmetric boundary states of the SL2R model and considering, gluing conditions of the SL2R model, and there you have different options, and these AdS2 branes correspond to taking some non-trivial outer isomorphism for the current algebra when doing this gluing, so that you get some time-like extension. Whereas this instantonic branes correspond to taking the trivial gluing automorphism.
I think what Clay's asking is basically what is the SL2 representation content of this, because they tell you how it looks like in AdS3. What was it?
Right. Okay. So I guess this statement that I call it as a AdS2 brane is a little bit dubious in this context, because of course it's a very non-geometric regime. So I mean, it's not so. I cannot. I mean, this cartoon is it's not completely reliable, and I cannot really identify a clear world volume of this brane, I think. But I mean, in a large scale regimes where you can make connection to geometric SL2R, you literally have a brane whose world volume is extended along a AdS2 subspace.
Is it the same? And Emil Martinez had.
Yeah, that's the next slide. So yeah, so
like a probe D string.
that's correct. Yeah. Yeah. So it's yeah. And anyway, so it's good that you point this out. So in that paper, there was no proper candidate found that could holographically describe these branes. But then there was the 2022 paper by Martinek, where he looked at AdS2 branes in a slightly different but related string background, which also involves symmetric product orbifolds in the dual. And in that paper, he gives a very nice qualitative description of some universal family of interfaces in symmetric product orbifolds, which he argues to appear in this context as a holographic tool.
Can you explain the picture on the left? What is the red dot?
Yes, so that's what I was just about to do. So this qualitative picture that paints essentially is that the dual should be some interfaces across which the size of the gauge group jumps from n minus to n plus. And this red dot I put here because then the question is, for instance, what would be the dual to some open string excitations, and you should try to reproduce the spectrum of open strings with the spectrum of local operators like this red dot that you can put on the interface. And that's precisely what we set out as motivation for our work. So we wanted to take this qualitative description and turn it into a quantitative description in which we can explicitly match the computations that you can do on the AdS3 side.
I'm also confused about the terminology interface in grand canonical ensemble, and then you have a specific n plus and n minus.
That's right. So for the simplicity of this picture, I put explicit n plus and n minus. And for most of this talk, I'm going to talk about how, first of all, you construct this as fixed n minus and n plus. Ultimately, we will then take a grand canonical ensemble of this, some average of this construction, and indeed have an interface really between.
I see. So you'll have some kind of interface that can go between all different n pluses and n minuses.
That's right.
And you take a sum of them.
Yes, and then there's additional parameters that describe this interface even at fixed n minus n plus, and these we also need to average over. But okay, we get to it. So yeah, as I said, the goal was to turn this into some quantitative framework, and in particular, the kind of the goal in this paper from April was to study the spectrum and to find something that fully reproduces the spectrum that you compute from the explicit boundary states given in the Gabadier paper. And in this current work in progress that I also talk about, we then went on to try and extend this also to scattering amplitudes and correlation functions in the presence of these interfaces, with the goal of reproducing the form of the Gauss expansion that we find in string perturbation theory. And this also is precisely the part where this grand canonical ensemble will be precisely defined. Okay. But before it makes sense to talk about any of these questions in more detail, I should establish some basics and say, first of all, what's a symmetric product orbifold in the first place? So that's simple. So a symmetric product orbifold is just you take any 2D CFT you like, you take n copies of it, and then this nth tensor power has a natural SN global symmetry, which just commutes the individual factors. And by gauging this SN symmetry, you get an SN gauge theory, which is the symmetric product orbifold. And when you do computation in the symmetric product orbifold, as usual in gauge theory, the evaluation, say, of some correlation functions will, of course, involve some sums over SN gauge bundles over the Riemann surface X on which you let your theory live. And what is nice about symmetric product orbifolds is that SN gauge bundles are in one-to-one correspondence with holomorphic covering maps, which are nice mathematical objects that have been well studied and which is useful for practical computations. This is why I'm now going to start by just reviewing some facts about holomorphic covering maps. In particular, the terminology that we need is dictated by the things from the gauge theory that we're interested in. So SN gauge bundles correspond to n-sheeted covering maps. The symmetry group of the gauge bundles correspond to groups of deck transformations. Insertion of SN monopoles that locally fix the structure of the gauge bundle correspond to operators that insert ramification of the covering maps, and the insertion of Wilson lines corresponds to measuring a monodromy of the coverings. So the things that I should define are coverings, deck transformations, ramification. So let's start with covering maps themselves. So an unramified covering map is a surjective holomorphic map between two Riemann surfaces, and sigma in this context is called the covering space. And if it satisfies two properties, so first we demand that locally gamma is invertible, and second we demand that every point in X has the same size of a set of pre-images gamma inverse of X as every other point. And if these two things are satisfied, we say that gamma is a degree gamma covering map, where the degree is the size of the set. So as an example, we could, for instance, just take the disjoint union of n complex planes to cover a complex plane, and the map we could take is a map that just forgets from which of the n copies a point complex number came from, and that's locally invertible because for every zi there's a neighborhood on which this is invertible, namely, for instance, just the entire ith complex plane. And on the ith complex plane, the inverse is just putting the label I on a complex number. And globally, however, it's not invertible. And in particular, every point in X has n pre-images, so the degree of the covering map is n. And now for ramification, so a ramified covering map is a map that if we take away finitely many points from sigma, from the covering space, would become an unramified covering map, in the sense defined on the left-hand side. And these isolated points at which we allow gamma to be to degenerate are called ramification points in this context. And locally around a ramification point, the expansion of the covering map takes the following form. So gamma of z plus delta is gamma plus z plus an order delta to the w term plus higher orders in delta. And this number w is something that classifies this ramification points, and that is called the ramification index of the map gamma in the point z. So in particular, a point in which a map is unramified and where gamma is locally invertible is a point in which the ramification index is 1. Well, and finally, what's the branch point? Branch point is just the image of a ramification point under gamma. So a simple example would be we take a Riemann sphere and we take the map that sends z to 1 plus z to a w. And outside of 0 and infinity, this is an invertible map. But at the points 0 and infinity, it has ramification with a ramification index w, as one can easily see by comparing these two equations. And the branch points are the images of 0 and infinity, so they're 1 and infinity. Okay. Next up, I also want to define symmetries of covering maps, so deck transformations. So what's a deck transformation? Well, it's an automorphism of the covering surface sigma, which preserves gamma, so which has this property that if we first apply phi and then apply gamma, it's the same as just applying gamma. So in the first of the two examples I showed you before, the group of deck transformations is just the Sn, which permutes the individual copies of the complex plane. Because if I act with some permutation here on this I label, and then forget what the I label is, of course, acting with this permutation has not made it. And for the second example, the group of deck transformations is generated by rotations by an angle of 2 pi n over w. So if I multiply z by an wth root of unity, of course the value of gamma of z doesn't change. So the group of deck transformations is zw. Okay, and before I move on, I want to show you a nice picture that I've taken from a paper by Bert Nice, which illustrates these things. So here he shows covering space sigma, which is again a two surface, X to be a sphere. He marked a bunch of ramification points in sigma and branch points in X. And in particular, he singled out one ramification point Z1 and one branch point X1. And locally in this neighborhood, the map looks like this. So every point that's at a generic point that's not the branch point has 4 pre-images in sigma. So we read off that this covering map is a degree 4 covering map. And okay, I should also say here these dotted lines are to be identified in the spiral that is a slice out of sigma. And at the branch point, this map degenerates, and there are not 4 pre-images, but just 1, which is at the axis of this spiral. And about monodromy, I just want to say very briefly that it is a prescription that using gamma allows us to take any point in X that's not a branch point, and then consider the set of pre-images of that point. And then for every closed curve that starts and ends in X, you can associate one permutation of the pre-images, essentially by following the lift of the curve to sigma. But that will only play a side role later on. Okay, so with this background, we can now very conveniently define symmetric product orbifolds. And by define, I mean I want to now give a prescription that allows you to evaluate the expectation value of an arbitrary observable of the symmetric product orbifold on an arbitrary Riemann surface X. By observable, for this moment, you can just understand any product of local operators. And how can we do this? So we take any observable and we assign to it 2 pieces of data. So first we assign a set of n sheeted covering maps, and that's how the n of the symmetric product orbifolds enters the construction. And then we assign a lift for each of these covering maps, and for each observable, well, for the observable, yeah, along the covering map to a new observable, which is an observable of the seed theory on the covering space sigma. And with this 2 pieces of data, you can then define an arbitrary correlation function like this. So this expectation value of this observable of symmetric orbifold on X is given by the sum of all the covering maps associated by this first step to this observable. And then for each of these covering maps, you evaluate the lifted observable of the seed theory on the covering space sigma. And this way you get some unnormalized correlation functions, and you can also define some normalized versions by dividing out the.
This includes twisted sector operators or not?
Pardon?
This includes twisted sector operators or not?
This should include twisted sector operators, and I'll get to it. But I'll first start with just the identity as an example. So if I take the vacuum operator of symmetric product orbifold, the identity operator, then the set of covering maps associated to it is just a set of all n-sheeted unramified coverings of X by covering space sigma. And the lifted operator is just the identity operator of the seed theory on the covering space sigma divided by the size of the group of Dick transformations. And what is kind of nice about this way of looking at symmetric product orbifolds is that this sentence essentially already tells us everything we know and already defines the entire theory, in the sense that because I left X to be arbitrary, you can take now the torus or genus 2 surface, and from this you can then construct, for instance, the entire spectrum or all the OP coefficients of the symmetric product orbifold. So as an example, we can consider the torus partition functions. We choose X to be a torus with modular parameter tau. and the potential, so the unramified coverings of the torus are just disjoint unions of tori, and the individual tori that can contribute are fixed to have a modular parameter that is related to the modular parameter of the original torus by a relation like this, with two positive integers w and l, and some integer k between 1 and w. And what this does is simply the w and the l count essentially a winding that you can use of the covering torus over the x torus along the two cycles. And this parameter k accounts for some additional shifting that you can do and tilting that you can do in this covering. And okay, you can explicitly determine these covering maps and so on and so forth, and use this to write down the torus partition function of symmetric product orbifold. And what you find is a kind of ugly formula, but I just want to highlight a single feature of this, namely that as I said, it has to consist out of all of these vacuum expectations of the seed theory on the covering spaces. So in this particular case, it will be some torus partition functions of the seed theory evaluating on these covering spaces with these modular parameter. So this is what appears here. And okay, another feature is that because we work at fixed n, and we have this extra constraint that the degree of the covering map should be n, the entire formula gets kind of ugly and has this extra constraint here that fixes some of the integers to n and so on and so forth. And this is the general feature of symmetric product orbifolds, and everything gets much, much simpler once you lift these constraints. So in this case, the way to lift the constraint is you introduce some chemical potential and you sum over this parameter n. And once you do this, the entire formula cleans up and it just simplifies all this nasty combinatorics with the different connected components and so on disappears, and just simplifies to an exponential where the exponent is just the contribution from connected covering maps. Okay, and from this formula, you can then directly go and read off the spectrum of the theory. So for every operator O of the seed theory, if it has a spin that is divisible by W, you get a W twisted version OW, which has conformal weights given by these formulas here. And by taking this description in terms of the covering maps for the torus and cutting open the torus, you can also figure out what the insertion of these operators has to do for the covering maps. So the insertion of this OW of X enforces a branch point at X with ramification index W. So it changes the set C associated to some observables to set of covering maps which has this additional ramification points.
Sorry.
And yeah,
These things you read off from which, like Z or the entire exponential expression?
right, you can read it up. Okay, I mean at a fixed n, what you could do is you could expand the right-hand side in terms of mu and look at fixed n, and then expand in terms of tau and see what the spectrum at fixed tau is. Or you can just keep mu in general and only expand tau, but you can.
Maybe my question is, these are spectrum at fixed n or?
This is a universal feature. So at any n, you get a spectrum like this. Once you fix n, this n is the upper bound for the value that W can take. So yes. Okay. Very good. And okay, I was just saying the insertion of this creates this ramification point, and then the other piece of data that was associated to the observables is how it lifts along the covering maps, and the lift of these twisted versions along the covering maps are just the untwisted operators from which they came from. Okay. Very good. So with this, we have everything that we need to construct these interfaces. And before we do that, however, I want to show you a kind of trivial construction of an interface that is qualitatively related, however, which is just a simple interface between two product theories where you don't gauge the Sn. So you can have n minus power of m on the left and plus power of m on the right. And you can pick any integer p between 0 and the minimum of n minus and n plus. And then you just identify the first p copies at the interface and just put the trivial interface. And for the other copies, you input some boundary conditions, and you can take different boundary conditions from the left and from the right. So here I could take a seed theory boundary condition a minus, and here a seed theory boundary condition a plus, for instance, for each copy. And the goal to have in mind now is that I want to build a version like this, a version of this in the symmetric product orbifold, where we have additional couplings to twisted sectors of the theory, so to this OW fields that we found in the symmetric product orbifold. And I also want to define these interfaces in terms of covering maps, just in the way that I've defined the correlation functions of local operators in terms of covering maps in the previous slides. Because this makes the computation of correlation functions ultimately straightforward. So, and the setup in which I want to do this is you again take some Riemann surface sigma and x, and again you demand that the boundary of x is trivial, but this time I will allow sigma to have a non-trivial boundary, and I fix a curve gamma inside of x, some closed curve, and its image is going to be some circle inside of x, like the red circle drawn here on the green Riemann surface x in this example. And what I want is that this circle splits the Riemann surface into two disjoint connected components. So here x minus and x plus. And the idea is then, of course, that we want to put the interface on this circle and then consider the different symmetric product orbifolds on the two disconnected components. Okay, but right now I'm just talking about covering maps, and the types of covering maps that I want to look at are again some surjective holomorphic maps between sigma and x that are locally invertible. But now we have this extra boundary of sigma, and I demand that this boundary is mapped to a subset of this circle. And additionally, I lift this constraint that the degree of the covering map has to everywhere be the same. And instead, I say that on x minus and on x plus, you can have different degrees, degree plus and degree minus. And lastly, an additional constraint that I put is for every point that is on this red circle, I consider a set of pre-images, and I look at the pre-images of the point that are in the interior of sigma. And I fix that this is always going to be the same number for every point that I take on the curve. And this number I call the degree of transmissivity of degree 0 of gamma. So for now, this is just a definition of some maps, and an example of this would be I could take x to be the complex plane, and as gamma to be the real line on it, or compactification of this. And I can take sigma to be a disjoint union of p planes, n minus p lower half planes, and a bunch of upper half planes. And again, I can consider the map that just forgets from which copy my points came from. And this has all the properties that we want. And, well, the restriction to the lower half plane, well, no. So every point in the lower half plane on X has n minus minus p pre-images here and p pre-images here. So in total, the degree on the lower half plane is n minus, and the degree on the upper half plane likewise is n plus. And finally, the degree of transmissivity of this map is just p, because all of the pre-images of elements of the real line that land in either of these half planes are on the boundary of sigma, and this degree of transmissivity counts those points in the pre-images that lie in the bulk of sigma. Okay. And so these are now unramified interface coverings, and as in the bulk case, we also should include ramification. And as opposed to the bulk, we now have a new situation where ramification points could either appear in the interior of the covering space or on the boundary. And of course, the ramification points on the interior behave completely as before, and in particular, they can be associated with the ramification index, which is again just a single integer. The ramification points that can occur on the boundary of sigma are slightly different, and on top of having some integer that describes their winding, they also have some additional labels which separate them into 4 classes. And the way to think about this is you can consider your covering space sigma, which has a boundary, and on the boundary you consider your ramification point, and then you take the curve that starts on the boundary, moves into the interior of sigma, and ends on the boundary on the other side of the ramification point in a clockwise direction, a counterclockwise direction. And then you can look at what happens to this curve, C of t, when you apply the covering map. And if the point is unramified, what's going to happen is that it maps one endpoint of this curve, C of t, to one point on the interface here. And then you go one way around and end again on the interface, but you don't cross the interface several times. But if you allow for ramification, you can additionally have the situation where you go around several times, and then the number of times you go around is an additional quantity that characterizes these ramification points. In addition to the information of on which side of the corresponding branch point your respective ends of the curve C are going to end. So on the starting points on the left and the end points on the right, I'll talk about the left-right point and so on and so forth. Where left and right is now with respect to some orientation chosen on the interface curve. Okay. Before going on to apply this now and to actually construct the interfaces, I want to make a brief comment for people that know the Riemann-Hurwitz formula for covering maps, which relates the Euler characteristic of the covering space to the Euler characteristic of X and the ramification of the covering map. So in our paper, we also prove some generalization of the Riemann-Hurwitz formula for our interface covering maps, which relates the Euler characteristic of sigma to Euler characteristic of these two halves, X minus and X plus, the ramification in the bulk, and these omegas as defined through this boundary ramification. And okay, this will not play an explicit role anymore in the talk, but it's implicitly behind the results that I show you because it's a useful tool in many computations. Okay. So now with that, I can actually define the interfaces. So I define some interfaces I, P, A plus minus between sim n minus and sim n plus, where the data labeling these interfaces is this pair of seed theory boundary states, A plus and A minus. and this integer p between 0 and the minimum of n minus and plus. And I put a curve on x as before, splitting x into x minus and x plus, and that's where I want to put my interface. And the goal now is that I want to show you how this vacuum expectation value of this interface is defined and how it's evaluated. And for this, I use the same approach as before. So I have to define a set of covering maps associated with these interfaces. And in this case, it's the set of all unramified interface coverings of X, which have degree plus minus of gamma being exactly n plus and n minus, and whose degree of transmissivity, P, is exactly this additional label that the interface carries. And then I also have to define how the interface lifts along the covering maps, and that's again just going to be the identity operator weighted by the group of deck transformations. But an additional piece of data that I need to specify when I say this is now what to do on the boundaries of sigma, because in this generalization now sigma is also allowed to have some boundaries. And what I do is, well, we split x into x minus and x plus. So if we take pre-images of this, this also splits sigma into sigma plus and sigma minus. And by taking the connected components of the boundary of sigma, which are contained in the connected components of the boundaries of these sigma plus and sigma minus, we get some distinction of these boundaries, and we impose a plus and a minus on these different distinct connection components. Right. Okay. And one thing that I'm not going into detail now in is that you can add additional information in this, so you can also now start thinking about what the monodromy around the interface is, and then you have some freedom to essentially dress these interfaces with some Wilson loops that allows you to add additional information from characters or representations of Sn plus minus and of Sp to the construction. But yeah, for the specific interfaces that are relevant for the holographic duality that I talked about, this doesn't appear, and these characters are just chosen to be trivial. Okay.
Can I ask a question?
Yeah.
Are these conformal interfaces?
Oh yes. Yeah.
Yes.
Yeah. Yeah.
How do you see that?
Mm.
They satisfy that.
Okay. So, I mean, one way to see it is now I give you this description in terms of the covering maps, and the nice thing about the covering maps is that this makes it straightforward kind of to compute correlation functions. But you can also, and that's also what we did, describe this just in terms of boundary states. So you can take the folded theory, and then you can write down some boundary state of the folded theory explicitly, and define the interface that way. And this makes manifest that they are conformal. And then the question is only how is this related to the thing that I defined by the interfaces. And to see that this is related, you can just explicitly evaluate torus partition function and so on via these boundary states, and then also via this covering map description, and see that the two things match.
If we go back to your description where you in the theory where you had not yet gauged Sn,
yeah.
If we just take the direct sum over of that interface over kind of permutations and then gauge Sn, is that the interface you're talking about?
Yeah. You take the direct sum over.
Right. In that
you take a direct sum over twisted sectors, but yes, yeah.
In that description, you sort of fixed P that you distinguish are going to be identified across, and then you ended at kind of n minus minus P of them, or n plus minus P.
Yeah.
And that description is not Sn plus or Sn minus symmetric, but we could have made it Sn plus or Sn minus symmetric by taking a direct sum.
Yeah. And this gives you one interface, but that's actually not the interface.
It's not this interface.
So this interface you would get this way would be the interface I described, dressed with additional Wilson loops that project onto the character that's only that's only 1 on the identity and 0 on everything else. So because you don't couple to extra twisted sectors. But what you can do is you can take the construction that you just referred to and additionally replace these copies that you identify and the copies where you put some boundary states by twisted versions. And then you need to think about, okay, how do I define P in this context? Well, you can define P as the sum over the length of the transmitted sectors. And if you do that, you exactly end up with the interfaces that I described. Okay. So, and with this, however, with this description that I gave you, the nice thing is computations are quite simple. And it's in particular quite simple to evaluate the torus partition function with two insertions of the interface, whereas which is description in terms of the boundary states and so on is a little bit painful. It can also be done, but yeah. And this is of course an interesting quantity to evaluate it because it gives us the entire spectrum of local operators we can put between two interfaces of interface changing operators. And so the only questions we need to answer now is what's the relevant covering maps that can contribute to this. So on the one hand, we can have just the covering maps that we have already seen in the absence of the interfaces, so just coverings of the torus by the torus. But then additionally, the covering space can now also contain some annuli. And for these annuli, you need to specify where the two boundaries that they have are mapped to. So you could either have both boundaries of the covering annuli ending up on the left interface, or both of them ending up on the right interface, or one on the left and one on the right, and so on. And this leads to 4 different sectors of these covering spaces. Maybe I should also say that, of course, in this way, we split the interface into 2 regions, the torus into 2 regions, and this gray region I put symmetric orbifold n minus, and this white region I put symmetric orbifold with n plus. Okay, so you have these 5 types of covering maps, and again, you could write down a similar formula like the nasty fixed n formula I've shown you for the pure torus partition function without interfaces. But in this case, it gets even worse because you have additional complications from this p left and p right. So I'm not going to do this. Instead, we'll this time directly go to the grand canonical ensemble. And so the 4 quantities that add constraints on our covering maps in this case are p left, p right, and plus and then minus. And to lift all of these constraints, we need to sum over all of these quantities. So we sum over these 4 quantities, and then we, for now, kind of arbitrarily assign some chemical potentials just in order to keep track of these variables so that later on we can expand in these parameters and recover the fixed p left, p right, and plus and n minus partition functions. Okay, and yeah, you can explicitly evaluate this grand canonical partition function, and again you find that it exponentiates as with an exponent that's the sum over connected coverings. And okay, this part is just literally exactly the same as the one that we've already seen for the case without interfaces, because this is just the connected coverings of the torus by the torus. And what is new is this part over here. And the new part is the one that comes from the coverings of the torus by the annuli. And you can explicitly write down what it is. So you find some combination, of course, of these chemical potentials that were introduced, but for now that's not so interesting. Then here you have the size of the group of deck transformations, okay? And what's interesting is then finally, what is the quantity of the seed theory that appears on the right-hand side? And the quantity of the seed theory is, of course, the annulus partition functions of the covering of the seed theory on these covering spaces that contributed here, where the modular parameter of these annuli are determined by these parameters of the covering maps. Okay, and they fall into 4 different sectors. And these 4 different sectors correspond again to whether you have both ends on this side, both ends on this side, and so on. And correspondingly, in each of these sectors, you find the respective seed theory boundary states appearing that went into the construction of the interface. So for instance, for this left-left sector, you find A left minus and A left plus from this guy. For the right-right sector, you find the analogous A right plus and A right minus for this side. And then there are the 2 mixed cases. Okay. So this function now contains the entire spectrum and all the spectral data. And again, you can expand it and look what you find. And okay, the conclusion is essentially, well, these local operators that are accounted for by the ZC are just operators that create ramification points of the covering map that are in the interior of sigma. So they are exactly the kind of ramification points we've seen before. And these 4 sectors of interface changing operators labeled by this A and B precisely reproduce these 4 sectors of boundary ramification points that I've shown you before. And in particular, if you now go and, I mean, all of this was for general seed theory M, but if you specify M to be T4 and you remove these chemical potentials that we've introduced just as counting parameters, then you find that this function ZO is precisely identical to the annulus partition function for open strings on AdS2 branes and AdS3 times S3 times T4 at k equal to 1 that you can compute with the boundary states of Gabardine, Knight, Bosmera. So on the level of the spectrum, you have strong evidence that this is a correct holographic description. You've reproduced the entire open string spectrum. Now, of course, we want to go beyond this and also study correlation functions. And there the question becomes relevant, what's the physical proper choice of these chemical potentials should be. And maybe just for organization, I should ask, because we started 15 minutes later, are we also extending or? Yeah, okay. Well, I already said that, already in bulk case, the grand canonical ensemble is necessary to create this connection to the Gauss expansion of string perturbation theory. So if you look at the expansion of string scattering amplitudes of NC closed strings, and look at the contribution of Gauss G worldsheets, you find scaling with the string scale like this, string coupling like this. Whereas on the CFT side, if you introduce this chemical potential exactly in the way that, well, okay, in the way that I did before when we computed the grand canonical partition function. So you multiply with mu to the n the contribution of the n symmetric product orbifold to a correlation function. Then you will find that the contribution of a covering space with Gauss G to the connected part of a correlation function scales with this chemical potential exactly with 1 minus G minus NC over 2 if you take NC twist fields. In this correlator, and the statement is for the case, of course, where the symmetric product orbifolds lives on the sphere. And therefore, if you just identify this chemical potential with G string to -2, you can structurally match the perturbative string perturbation theory. And then furthermore, you would also have to explicitly match these contributions to the scattering amplitudes and correlators, but this has been done as well. And more generically, you can even consider cases where you would have some locally AdS manifold M whose boundary now might have a more complicated structure and some genus G that's not zero. And then correspondingly on the symmetric product orbifold side, if you pick this chemical potential to scale as G string to the 2G minus 2, you again are able to reproduce the expansion. Yeah.
Oh, can you go to the previous slide?
Yeah.
Oh, sorry, maybe I missed. Mu plus minus is what? They are not the chemical potential, right?
Right, mu plus and mu minus were the chemical potentials that I had introduced here for n plus and n minus. But at that point, these chemical potentials are kind of bad. They are just some arbitrarily chosen chemical potentials. And the point that I want to make now is that in the bulk, there's a preferred way to choose these chemical potentials. And in the boundary, there's also a preferred way, but it's not the way that I've just shown you. It's the way I'm showing you on this slide.
Oh, I see.
Okay. And so what we show is that if you choose your chemical potentials to correspond to the quantities n plus minus p and the quantity p, so you introduce nu plus minus and chemical potential mu for p, and look at correlation functions in this setup with a single insertion of the interface on some genus G Riemann surface that splits into genus G plus and genus G minus halves. Then you find that, again, you can precisely match the string perturbation theory by now fixing this chemical potential mu to be G string to the 2G minus 2, and nu plus minus to be G string to the 2G plus minus 1, which then gives you, this expected scaling, where here and C and NO on the string side are of course counting closed strings and open strings, contributing to scattering amplitude, and G and B are genus and the number of boundaries of the worldsheets. And here on this side, again, G and B are genus and boundaries of the covering spaces, and C is the number of bulk fields that creates these ramification points in the interior, and NO is the number of fields that create these boundary ramification points.
Sorry, maybe again I missed it. U plus and minus are related to mu plus and minus in which way?
Again?
U plus minus? They are different from mu plus minus, right?
So I introduced nu plus minus as chemical potentials for n plus minus p.
Oh, I see.
So I mean, you have these, in this case, so before we talked about torus with 2 insertions of the interface, so there were more parameters. Here it's just 1 insertion, so we just have this parameter p of the interface, and then n minus and n plus. And then the question is, what should the chemical potentials be that control the average over these parameters p and plus and n minus? And what you find is, okay, it's not correct to take a chemical potential for n plus n minus and for p, but instead you should take chemical potentials for n plus minus p and p if you want to have some natural formulas. Yes. So in this sense, we can fully reproduce the structure of string perturbation theory, but to really be able to say that we precisely match the partition, the scattering amplitudes, we now, of course, would also have to evaluate these contributions here, and likewise evaluate these correlators and establish the match. And that's still left to do. So to sum up, we, in this paper from April, got this construction of universal interfaces, universal in the sense that they appear for any seed theory of a symmetric product orbifold, and we fully classified all interface changing operators and matched the unless partition function for the open strings and the AdS3 brane. And in our paper that we're currently writing up, we developed this whole covering map machinery describing the interfaces in terms of these generalized interface covering maps, and which allows you to efficiently evaluate the correlation functions, and which also allows us to derive this structural match and identify what the correct chemical potentials should be to connect to string perturbation theory. And for the future, as I said, we want to also evaluate these explicit contributions to fully match the open string amplitudes. And furthermore, there are a bunch of interesting deformations of symmetric product orbifolds, interesting from the bulk perspective, that we'd like to also study with our interfaces. Right, so at this point, there's nothing left but to say thank you again for listening to me. And are there any questions? Questions?
Actually, can you go to a slide where you had the open string spectrum, like where the like u plus minus equals 1?
I mean here?
Next one.
Yeah.
Sorry, can you explain why you set this to be 1 to make the comparison?
Right. So, I mean, the point is that when we make this comparison, what we really compare is just this exponent. And this exponent only comes from connected coverings of the torus by an annulus, right? Now, on the string theory side, this means that what we compare to is something that only has contribution from annuli also. And therefore, we don't really see the dependence on the string coupling because, well, we only have one type of topology for the worldsheet. And therefore, we can also not really see what the physical interpretation of these chemical potentials should be, because these chemical potentials are ultimately, fixed in terms of string coupling. So somehow this match is not good enough to really see what the chemical potential should be. And these chemical potentials in this match just disappear in some normalization constants. So therefore, here we just set them to 1 in order to do this match. And later on, if you want to, really see what the physical chemical potentials are, you need to look at more complicated correlation functions.
Yeah, I can ask later.
Okay, okay, let's thank the speaker. Thanks,